Hello friends, hope you are doing well in your Six Sigma journey, and step by step we are advancing in our DMAIC Six Sigma cycle. So we are discussing analyze phase of Six Sigma cycle, and as a part of that, in the last lecture we had seen the concepts basics related to correlation and regression analysis. This is lecture 33. We will focus on regression analysis model validation. So, if you just see this beautiful quote given by Mark Twain, that facts are stubborn but statistics are more pliable. So, here we should appreciate that when we want to be scientific in our analysis, pliable means statistics are flexible. The way you set your null hypothesis, alternate hypothesis, the investigation, that will move your investigation in that particular direction, and many a times you do not really reveal the meaningful, insightful information results because the considerations whatever you have taken into account are not valid, like length of Mostak and the increase in sales, there is no relationship. Like diverse rate and maybe the sales of the butter, there is no relationship. So, facts are stubborn, they do not change, but statistics are more pliable and we should be cautious. So, with this quote, I would just like to give you a small recap and introspection that we discussed the correlation analysis, regression analysis basics about predicting the value of dependent variable based on set of independent variable. But if you recall, I mentioned that you need to say understand the quality of the regression model, and this is about validating my regression model. So this particular lecture is dedicated on validation of regression model by performing various kind of tests and to see that to what extent my model is really capable of predicting what it should predict. So, I will try to focus on validation of the regression model, and as a part of that we will see autocorrelation, Durbin-Watson statistics, t-test, f-test, some of the pitfalls of regression analysis, and I would also like to present the simple Minitab application for conducting regression analysis. So just try to appreciate that when we are trying to minimize the sum of square of error, which we did last time, and it was basically this particular component. This is what we try to minimize, and this is what we did in the last lecture. So basically you have SST, this is SST, this is SSR, and you have SSE. So basically your total sum of square, if we just decompose, then it is SSR, that is sum of square of regression, and SSE, that is error sum of square or sum of square of error, and you have Y bar. So Y bar is mean value of the dependent variable. Very well intuitively you can understand that individual observation minus Y bar, mean value of the dependent variable, that is the total say sum of square variability. Yi is observed value of the dependent variable, and you can see here that yi minus y bar whole square, this is typically related to your predicted value yi hat minus y bar. So this will be the error specific to sum of square specific to your regression, and when you see this is your SSE, sum of square of error. So this is the expression that typically relates your SSR, SSE and SST. Now what I said I just summarize here. that SST means total sum of square, that is the total variability, and measures the variations of the yi values around their mean y. So that is y bar. SSR is regression sum of square explained variation, and this is variation attributed to a relationship between x and y, how well the relationship between dependent and independent variable is defined. So this particular phenomena is captured through SSR, and SSE basically error sum of square, it is the unexplained variation. So variation in y attributable to factors other than x. So typically you may consider some of the exogenous factors, external factors, unknown factors that may have impact on your regression model, which you are not able to actually capture, and this is your SSE. So this R square, basically we have seen that coefficient of determination R square is a very important measure, and this is basically the ratio of your SSR and SST. So regression sum of square and total sum of square. So this particular measure is a very important measure, and this measure is basically used to explain the proportion of the total variation in the dependent variable, your left side variable, that is explained by the variation in the independent variable. So again I would just give you the example to make it clear that I want to judge, I want to predict that what are the factors that contribute towards the productivity of my manufacturing process. So let us say productivity is my dependent variable, and it depends on couple of independent variables like process capability, my training and skill of the operator, state of the art technology, management policy. Now when I am trying to figure out the relationship between productivity and these other independent factors, then I want to see that how well the portion of the total variability in the dependent variable, here it is productivity of the manufacturing process, is explained by the independent variables like worker and training skill, say training skills and the worker skills, or the management policy, maintenance schedule, state of the art technology, and so on. So I have R square is equal to SSR divided by SST, and typically this should fall within the range of say 0 to 1, and this term is very important to understand that to what extent my regression model is capable enough to capture the variability, and this variability should be explained by the various independent variable in the regression model. So with this little understanding, just try to see, because visual say display can help us better. So you can see that approximate R square values, and you are trying to say see the relationship between x and y, and what you can see that there is a perfect linear relationship, whether positive or negative, but there is a perfect linear relationship. 100% of the variation in y is explained by variation in x. So in my words, I will say whatever independent factors you have included in your model, they are 100% capable enough to explain the total variability in the y, and there are no other factor or exogenous factor which really have an impact on the quality or prediction ability of my regression model. So this is a very important term, and we must try to appreciate this term in the validation of the regression model. Now you just see here, this is the situation where you have the scattered plot, you have a line explaining the relationship. Now in both the case you will see that weak linear relationship. So I would say that some but not all variation in y is explained by variation in x. So, either you have not considered adequate number of independent variable which can explain the variability in y, that is your dependent variable, or there are some exogenous factors which you are not aware of affecting your model, and hence your variability is very high and the relationship is weak. So, this is the importance of R square in judging the quality of my regression model, and this is the case where you can see that your R square is equal to 0. So, no linear relationship between x and y. You cannot predict the y using some independent variable x or xi, and no variation in y is explained by x. So, this is the third case where no variation in y is explained by x. Now, there is another term. I am just trying to familiarize you with some fundamental concepts in validating the regression model, checking the quality of my regression model. There is another term which is called adjusted R square. So, many a times what happens that an analyst in its desire to improve the value of R square may keep adding many independent variables regardless of their relevance to the model, and by doing such kind of manipulation you may end up with very high R square value. So, there is a way, and there is another measure which is called adjusted R square. So, this typical measure adjusted R square is basically used to check even the truth explained by the R square, and this particular measure adjusts the statistics based on the number of independent variables in the model. So, I would say you can game R squared by adding more and more independent variables irrespective of the relevance or how well they are correlated to your dependent variable. Obviously, this is not a desirable property of a goodness of fit statistics. So, when you are trying to check the quality of your regression model, you will not only see the R square value, you will also see the adjusted R square, and many a times say if the adjusted R square is very low, then you need to revisit your assumption about the independent variables or the relevance to the dependent variable, may modify your model and see that the R square value and adjusted R square value both should be favorable, adequate enough to express the goodness of fit of my regression model. So, as I mentioned that adjusted R square provides an adjustment to the R squared statistic such that an independent variable that has a correlation with y increases adjusted R square, and any variable that has a strong correlation will make adjusted R square decrease. So, this is where say I would like to make the adjustment to my R square and see that what is the real R square, and simply I will not get governed by the value of R square. So, this is the property of goodness of fit to the test, and if you have a relation, if you have a variable without a strong correlation, then it will decrease the adjusted R square. So, there is a trade off. If your dependent variable has a good relationship with the independent variable, it will increase the R square, it means adjusted R square. If not, it will decrease. So, this trade off is taken care by adjusted R square, and that will help you to even verify your R square value. So, now we talk about the model validation of regression model, and we must check the regression model against the fundamental assumptions, and these assumptions are called line assumptions. Line assumptions stands for line, L stands for linearity. The relationship between x and y is linear. If you have say non-linear relationship, then the kind of model linear regression you are using will not really have the capability to predict what you are trying to say investigate or predict through this analysis. Independence of errors. So errors were statistically independent. It means there should not be any hidden phenomena because of which there is some kind of relationship or dependence within the error, and if my errors are independent, then this is the second assumption which is satisfied, that is the independence of error as a part of line. The third one is normality of error, that error values must be normally distributed for any given value of x, and finally equivalence of variance, also called homoscedasticity, and this is the probability distribution of the error that has the constant variance. So these four assumptions must be checked, must be verified if I have to accept my regression model as a good predictor for the phenomena under consideration. So you see that how can I compute the residue? So it's very simple. There is an observed value, there is a predicted value. When I take the difference between these two, observed and predicted value, I get the error component for a particular value of I. So yi. Now we want to check these assumptions. As I mentioned, these are the line assumptions, and we can first do the graphical analysis of the residue to immediately get an idea that to what extent my line assumptions are valid or they are satisfied. So just see that how we can interpret the line assumptions. This is my residual analysis for linearity, and this is the first one where I can see some pattern. So this pattern is depicted here, and this is the curvature, so not linear. But if I see this scattered plot and if I see this, then I can say that linearity is present. So when I plot my residual with respect to say my observed value or xi, and when I plot my y value with respect to x and see the plot, I get an idea about the linearity assumption. The second one is independence in line. So you can see here very well that you can see here that the first case, these are not independent, and here also you can see that it forms some pattern and there is ups and downs in my error component, residual component, and these are independent because there is no pattern available. This is just the random variation, and my independence assumption can be visually verified. Now the third one, which is very important, is checking for normality. You have various options available, that you can examine the steam and leaf display, you can examine the box plot of the residual, you can examine the histogram, and most widely used approach is the normal probability plot of the residual. So these are the various approaches. First three we have already seen. Even in process capability analysis, normability plot we have plotted for the normal and non-normal data to check that whether my data set is normal or not. So these methods can equally be applied for checking my normality assumption for regression model, and you can see here that the normality plot, when you put or plot the values of residual with respect to percentage. So basically it's a classically designed normality plot where you try to plot the values of residual with respect to say your Z value, probability value, and if these points are covered by a pencil or pen, then majority of the points you will say that normality is present. So this is the approach which is widely used to check the normality. And the final one of line, that is the E, and equivalence of variance. So if you see the first case, then non-constant variance and you have the constant variance. Here you will find something like a funnel approach. For residual, again you will find a funnel approach. Here it is a constant variance over a particular range. The variance is not changing significantly, it is just random phenomena, and I have the idea that whether my equivalence of variance is satisfied or not. So this is how I can check my line assumption. And when you are using Excel or Minitab, your software will generate the different display that can help you to understand that whether your line assumptions are satisfied or not. Now let us try to go into detail, because whatever I presented, it is mainly the visual, say, observation about my line assumption, but I also want to do some inferential analysis to check the prediction ability of my regression model, or in the simple word, quality of my regression model. So the first one is to measuring autocorrelation. So this is particularly the concept, or autocorrelation is used when data are collected over a period of time to detect if autocorrelation is present. Is there any correlation among the data is present, maybe because of some factor, and if autocorrelation exists, if residual in one time period are related to residual in another time period, then we can say that autocorrelation exists, and this is not desirable. So far the regression model is developed based on this kind of data set. So you can just think about a situation that there is a continuous wear and tear because of some misadjustment in your process, and whatever data you are getting, which you are using for predicting or developing the regression model, is some way autocorrelated, and if your data set used for developing the regression model itself is some kind of biasness phenomena prevailing, then it will have an impact on the quality of your regression model. So I would like to check this, that whether autocorrelation is present or not. So you can just see that when I am plotting the residual with respect to time, I can see that I can just little bit shift this particular graph above, and you can see that this fits like this. This just you can put it like this. This would be better, I think, and you can get an idea that yes, there is some cyclic pattern which is present. So here your residual, they capture this, the pattern when these residual are plotted over a period of time, and they show the cyclic pattern, not random, and there is a sign of positive autocorrelation. So this violates the regression assumption that residuals are, say, random and independent. So previously we have tested this assumption simply by having the graphical, say, display. Now I am trying to see also the alternate approach, inferential approach, to be more accurate about my say assumption. So the first thing that you plot, and just a visual display can help you to appreciate whether there is any kind of autocorrelation prevails or not. Now if we go into the inferential testing of autocorrelation then there is a test called Durbin-Watson test, and this test basically, like all other tests, we must have a test statistics and we must set initially the null and alternate hypothesis. So this particular test used to infer about the autocorrelation among the data says that residuals are not correlated, H1 there is a positive autocorrelation present. So there is a Durbin-Watson statistics which is quite simple to interpret. You have EI values for each particular, say xi, yi, you have EI, and you have EI minus 1, that is the previous value, and you have EI square. So the possible range for this is 0 less than or equal to d is less than or equal to 4, and d should be close to 2 if H0 is true. So these are the standard guidelines developed, and if d is less than 2 may signal positive autocorrelation and d greater than 2 may signal negative autocorrelation. So we accept the standard guideline to infer about the autocorrelation present in my error data, and I would like to statistically infer that whether there is an autocorrelation present or not. So this way I can just move ahead. Now let us say you have a regression model like this, and this is typically say expressed like y is equal to 30.65, that is the intercept, plus 4.7038x, and my r square is 0.8976. So is there a autocorrelation, or this is just my say doubt, suspicion? I want to check it statistically. Now just see, I computed the Durbin-Watson statistics using Excel. You can do it in Minitab also. So I have, or I can compute it manually also. So Durbin-Watson statistics is 1.00494. This is the sum of squared difference of residual, sum of squared residuals, and this is 1.00494. So if we refer our guidelines, then what does it tell? So I have the situation like this: n is equal to 25, k is equal to 1, Durbin-Watson table. So like Z table, T table, you have the Durbin-Watson table that you will find in the suggested textbooks. You can find DL and DU, and you can set the rule like this, that if your computed value of Durbin-Watson statistics is less than DL, then you reject null hypothesis. If it is in between, you are inconclusive, you cannot comment whether autocorrelation is present or not, and here you do not reject null hypothesis. So here the kind of data set I have assumed, I fall into the region which is less than DL, and I will say reject null hypothesis. It means there is some autocorrelation present. Now you can also make statistical inference about the slope. So you have the SB1 Sxx divided by square root of Ssx, and this particular expression can help us to compute the SB1. So SB1 is estimate of the standard error of the slope, and Syx sum of square, that is square root of SSE sum of square of error divided by n minus 2. Now when you do this, you can compute your inferential statistics, which is the t-test, for checking the relevance of the slope, that is beta 1, for your regression model. So please remember that we want to compute beta 0, we want to check the validity of my regression model, which is dependent on the beta 0, beta 1, beta 2, beta 3. I want to see that whether my slope is statistically significant or not. So I would set the null hypothesis beta 1 is equal to 0, beta 1 is not equal to 0. So no linear relationship exists, and I would say linear relationship does exist. So, this is my premise of testing the beta 1, and I can set the test T stat B1 minus beta 1 divided by SB1. So, B1 I would refer as regression slope coefficient, beta 1 hypothesized slope, and SB1 is the standard error of this slope. So, with this particular test statistics T, I can verify my assumption or my understanding about the beta 1. Let us try to take an example. So, the example goes like this: you have the house prices in dollar, maybe 1000s, and you have the square feet. I am only considering two. One is the independent variable, that is my square feet, and the other is the dependent variable, that is the house price. Now, my equation, regression equation, comes out to be house price 98.25 plus 0.1098 square feet. This says that these two are related like this, and I can predict the house price based on this square feet. There could be many factors which I have not considered here, just to explain the pitfalls or some of the errors that you may cause in conducting regression analysis. Now, you just see here, just by observation I can say that if I put square feet is equal to 0, even though I will have to pay some 98.25 thousand rupees for not purchasing the house. Square foot 0 means I am not purchasing the house. Who will accept such a model? I am paying some lakhs of rupees to my builder, some builder, for not purchasing the house. So, beta 0, my intercept has no value here, and this can even be validated, tested through inferential statistics. So, just try to see that I can compute this beta 1. So, this is the Excel output. You can do it in Minitab also. This is my SB1, and I can compute the T statistics beta 1 B1 minus beta 1 divided by SB1. This comes out to be 3.329, and I can make the inferences about my hypothesis beta 1 is equal to 0, beta 1 is not equal to 0. So, what I would say that the alpha by 2 is 0.025, and I have the computed value 3.329, which falls within the rejection region. So, decision is reject null hypothesis. This says that there is sufficient evidence that square foot affects the house price. It means my particular assumption about the relationship between square feet and the house price is true, and the inclusion of this independent variable will help me to explain the total variability present in predicting the dependent variable, that is y. So, now let us move ahead, and I can also check the p value. So, again you can see that p value is less than alpha, and I can reach to the same conclusion. Now, you can also conduct the F test for significance, and as you know that F test is basically MSR divided by MSE. So, mean square of regression, mean square of error, and when I compute this, SSR divided by degree of freedom k, SSE divided by n minus k minus 1. So, F state follows an F distribution we have studied, and k is the number of independent variables in the regression model. So, I can also do the inferential analysis about the quality of my regression model, and what I am trying to do here, I have computed the F stat, and I have, let us say, residual degree of freedom 8. I have p value computed for F test is 0.01039, and I do have the value F 11.0848. So, with this particular result, what I am trying to investigate is that whether my assumption about relevance of the beta 1 is true or not. So, H0 says beta 1 is equal to 0, alternate says beta 1 is not equal to 0. For the computed example, my f.05 is 5.32, which is the critical value, and this is my region of rejection, and my computed value f stat is 11.08. So as I am counting from 0 onwards, so this is much higher and it falls much higher than 5.32 and it falls in the rejection region. So your conclusion is that reject null hypothesis at alpha is equal to 0.05, and there is a sufficient evidence that house size affects the selling price. So you can check it through t-test, you can check it through f-test, and you can better make the inferences. You can also set the confidence interval, and we have 3 different approaches through test hypothesis. You can also apply the confidence interval approach. You can compute at lower 95, upper 95, and this is the confidence interval you create, and you can check that whether your beta 1 or B1 is falling in this range or not. So this is what is about confidence interval we have already done. Now you can have t-test for correlation coefficient. So you have rho is equal to 0 as null hypothesis, rho 1 is equal to 0, and you can set the t statistic as r minus rho. So r is basically related to your sample, rho is related to your population, and this is the value of standard deviation for conducting this test. So if you have, let us say, n minus 2 degree of freedom, and r is basically plus square root of r square if b1 is greater than 0, it would be minus square root of r square if b1 is less than 0. So for this particular kind of approach, that to check the correlation coefficient, I can have the hypothesis rho is equal to 0, rho is not equal to 0. I would be interested to check it at alpha is equal to 0.05, degree of freedom 10 minus 2 8, my computed statistics is 3.329. Now if I just go further, then this 3.329 basically falls in the reject region. This is my T alpha by 2, which is the critical value from the table. So my decision is that reject null hypothesis, there is an evidence of linear association at 5% level of significance. So this is what I can do. I would just like to sum up with couple of pitfalls in regression analysis. So looking an awareness of the assumption underlying least square regression. So this is something lacking, that we are trying to do it under least square say method. So this awareness is one of the part that we are trying to minimize the sum of square of error, not knowing how to evaluate the assumptions. Many a times you just feel happy with the outcome of your software, but you do not really go into the detail of checking the line assumption, and this is where the prediction ability, quality of your model is at stake. Not knowing the alternatives to least square regression if a particular assumption is violated, and we have discussed that what are the various ways you can better make yourself clear about the assumptions. Using a regression model without the knowledge of the subject matter. So like length of the Mostak and the increase in sales, you do not exactly know that what are the factors that can affect the sales or the Mostak, and you just try to manipulate with the situation. And remember, you cannot set the regression model for a universal range. So exploding beyond a particular range will again have a negative effect on your prediction ability. So there are certain strategies for avoiding pitfalls. Start with a scatter plot, try to see whether there is some relationship exists or not, perform residual analysis, conduct the various tests for autocorrelation and checking the significance of beta 0 and beta 1, and then you can better feel confident about the quality of your regression model. Just to share quickly the Minitab application of linear regression. we have an example that an educator wants to determine whether students' exam score were related to revision time. So, you will also have an exam for this Six Sigma, and we will go through many lectures. There would be more than 60 lectures, and you will find it difficult to revise. So, I would advise that right at this stage, when you are going through the lecture, please make your summary note which you can revise very quickly at the time of exam. So, here in this example, teacher educator is interested to see that whether there is some relationship between the revision time and the student score in exam. So, here suppose the student spend more time revising, did their exam score increase or did the opposite happen? Sometimes opposite may happen. The educator also wanted to know the proportion of exam score that revision time could explain. So, total variability to be explained by the independent variable in the dependent variable, and he basically collected the dependent variable was the exam score measured on a scale of 0 to 100, and independent variable is the revision time. So, we want to carry out this analysis and recorded the revision time exam score of 40 participants, and just try to tabulate this in the Minitab or Excel sheet and then borrow it. So, C1 we entered the dependent variable, that is the exam score, C2 is the independent variable revision time. Now, just see how it is easy to perform regression analysis in Minitab. Go to stat, see the regression, then you will have a drop down window regression, fit regression model. Just doing this, after doing this, you will have this kind of window where you will see the response variable to be entered, continuous prediction, categorical predictor. You have basically two, exam score as the dependent variable, revision time as the independent variable. So, once you have this window, then you can choose this from this particular say window and put it here, exam score revision time. Then you click OK and you will have the output generated. So, you can see here that you have the source of variation, degree of freedom, adjusted sum of square, adjusted mean sum of square, f value, p value. So, regression, error, total, you have the p value. You can check whether your beta 0, beta 1 they are significant or not. Here you have the coefficient and corresponding p value. So, constant and revision time, and you have the regression equation set, that is exam score is equal to 42.86 plus 0.5756 into revision time, and you have also the values of r square and adjusted r square. So, you can see here that r square and adjusted r square are very close. So, whatever independent variable I have, that is revision time, it is really able to explain the variability in the dependent variable, which is the exam score. So, this analysis you can do very easily, and you can interpret as I explained what is adjusted r square, what is r square, what is coefficient column, and you can interpret the results like this, that r square is equal to 80.87%, adjusted r square is 79.6, no issue with the quality of the model. R square estimate 79.6, so it is a indicative or a large effect size, and you have the p value 0.0005. So, this indicates that overall the model applied can statistically significantly predict the dependent variable, that is the exam score. So, think it before we end. What is the goal behind autocorrelation study? What is the significance of t-test? What test is adapted for model significance testing? What is the goodness of fit in regression model? How it is calculated? Why researchers have developed adjusted r square, and what are the assumptions of regression line, how these are tested. So, use these references for your better understanding and revising the concept. Correlation is used to test if residual in one time period are related to residual in other period. t-test if there is any linear relationship between dependent and independent variable, f-test checks the validity of null or alternate hypothesis for my regression model. And with this, I would say that this lecture you should revise appropriately. If necessary, try to revise it twice, strengthen your understanding, and with this, thank you very much. Do well in your day-to-day studies, profession, and try to now visualize the application of Six Sigma in some of the facets. So here now you should try to define some of the problems in your day-to-day life, in your organizational setting, where you would like to apply DMA IC cycle for the improvement. So with this, thank you very much. Be with me, enjoy.